a lovely lunch, and if you weren't there, we enjoyed some Japanese food, and we enjoyed some great conversation. We had, I think, a chance to informally talk a little bit about what we're seeing in embedded automotive and consumer electronics. Now, the first topic as we start this afternoon is the embedded space. And that's obviously going to be very important in a place like Japan, where we have a lot of companies doing embedded technology. One of the key questions around embedded is always, how do we go from, sure, this is an interesting technology, through to, yes, I'm going to put this in my product, and my product will go to market in reasonable time, and I can support it and rely on it. There are many choices when making embedded technology. Traditionally, we've rolled our own. More recently, we've tried to use shared platforms. But there's no winner in the market space of shared platforms. Everyone has slightly different needs, and nothing solves all the needs. Quite a few companies have talked to me about the way that they're in the middle of transition. Some of them are using old proprietary embedded platforms like QNX. Some of them were using totally custom Linux distros or similar. And a lot of people are trying to move to the next step of more sustainable embedded platforms. So we're going to have a look at how openEuler approaches this with the mindset that, as you saw this morning, openEuler is process heavy. It's working from the beginning and trying to make things manageable, trying to have clear ways to approach records, bill of materials, compliance, security. Exactly the type of approach that we want to learn more about when we're thinking about a product that maybe will be in market for 15 years. How do you keep track of that? 10 years later, when everyone's moved on, how do you double check? How do you support it? How do you update it if necessary? Some of our companies, like I believe on the line at the moment, or coming in soon, we'll have some people from Hitachi. And I remember one interesting conversation with a colleague from Hitachi Madison. And we were talking about trains, because Hitachi makes the Nozomi Shinkansen. And the support cycle is 30 plus years. And that means when you build one of those, whatever is embedded in it, you have to be ready to support that for 30 or more years. And of course, other companies like Hitachi or Toshiba are building nuclear reactors. And there you're looking at 50 years or more support cycle. So it's a very interesting challenge. And certainly it's a very different challenge to Silicon Valley, where, you might think, oh, we'll go to market and see what happens. You can't do that on a train traveling at 300 kilometers an hour that's 25 years old. So let's have a listen. Let's have Wayne come to the stage and talk about embedded in openEuler, and let's see how it's done. Let's understand what the processes are there. I'm going to unplug my laptop, so the rooms video will change, but I'll keep screen sharing for a minute and then let Wayne take over. There you go. And if you could share your screen, Wayne, it would be great. Yes. Some of the participants online want to see the shared slides in detail. Sure. Okay. I think it's okay. Sure. While Wayne's getting ready, I'll tell a story. 4 days ago, I was in Taipei, and I got a bunch of pineapple cake. And for those of you who are in the room, they're just at the back there. They're from one of the most famous pineapple cake makers in Taipei. Highly recommend it. It's so addictive. But pineapple cake is about 350 kilocalories per cake, even though they're tiny.
Just a warning, if you're on a diet, don't do it.
So is everybody okay? Okay, so because this event is held in Japan, so まず日本語でご挨拶します。私はニーと申します。15年前に、2010から2009まで名古屋大学で、高田先生の研究室に、組み込みシステムを勉強しています。今回はこのイベント参加できるのは、これは私の光栄です。しかし、私は日本語はここまで。原因は全部で日本語は発表します。全然無理です。So, I will use...
Hold on. I will ask the Japanese. Does he speak real Japanese?
どうでしょう問題はない。
It's okay to understand Japanese?
Yeah, very good Japanese.
Very good Japanese. We'll switch to English.
それはダメです。これは日本語では発表は全然難しいですけど。Okay, I will change to English. Okay, it's my great pleasure to share openEuler embedded, an open and comprehensive embedded software platform. Okay, there are two parts of my talk today. First is the general introduction of openEuler embedded. The second part is a very critical feature of openEuler embedded. We call it MICA, Mixed Criticality Framework. Okay, so Dr. Sean already made a brief introduction of openEuler embedded in the morning. And openEuler is an OS platform for all scenarios. So from IT technology to all, and including CT and to OT. OT means operation technology. So, and in the field of OT scenario, openEuler embedded is the one to cover this scenario. So we share everything that can be shared among different scenarios, like kernel, like infrastructure, like SBOM, like CV, everything that can be shared. But the difference is that how we make it, because in embedded systems, the requirement is totally different with standard IT scenario. So in the IT scenario, everything must be standard. We have standard machine, and we have BIOS, right? And we have a standard image. But in embedded system, everything must be customized according to different requirements. For example, maybe I have different hardware and I have different scenarios. I can use it in high-speed railway, like Shinkansen. You can use it in, for example, PLC controller, and their requirements are totally different. So for embedded scenario, a very important requirement, just customization, right? So the difference is that we are just like different cookers. We use the same stuff, food, but we make different style, right? So this is the difference. And we just also are very young. We are young brother in the big, middle brother in the big openEuler community. And as we know, openEuler starts from 2019, but we start from 2021. And we just 2 years old and 2.5 years old. So this is openEuler embedded. Next, okay, this is a general layout about openEuler embedded. It looks like a solar system, Tioke. And the center is the Linux, comprehensive platform. And there are a lot of planets, like we call it, for example, Earth, like Moon, like Jupiter, but we call it a TE, real-time operating system, bare metal embedded virtualization. So why do we define such a layout for openEuler embedded? The reasons are because we can notice that on one hand, even for embedded systems, the application is becoming more and more complex. You need more and more features. I need, for example, connectivity, a smart human-machine interface, and now AI. So we want more features. And so complex application required complex software platform to support it. But because you cannot just implement everything in a bare metal environment, that is impractical. This is one reason. Another reason think about the change of hardware in the past 10 years in embedded systems. For example, 10 years ago, when you're talking about embedded system, you may refer microcontroller, right? 8-bit, 16-bit, and even 32-bit is very strong. But let's think how it's going on in these 10 years. The embedded hardware is becoming more and more powerful, especially in the automotive electronics. In the past, okay, ECU, the automotive electronics means a lot of ECU are connected together. But let's see what's going on in the current automotive electronic industry. Domain controller, central controller. It means that the strong hardware can support complex software. So that's why, in the past decades, Linux is more and more popular in embedded systems, from consumer electronics and to some traditional fields of real-time operating system, like train, like satellites, right? So like vehicles. So we are convinced that Linux will be more and more popular in the embedded systems. So I think that is a critical part. But what makes embedded systems different with the common IT system, that embedded system has to face a lot of constraints, like security, safety, real-time reliability, a lot of factors. And some guys want, okay, can I just meet this requirement, just use one Linux? So this is a lot of people are trying this, but I think that is very, very difficult, because even Linux also admitted that Linux kernel is not designed for these scenarios. So, but how to handle this, specific requirements of embedded system, like real time, like safety or whatever. So we use, some small OS or small runtime. For example, if you want extreme security, for example, okay, your fingerprint or whatever, we can rely on the trust execution environment, TEE, which is very popular in ARM and in our current mobile device. And if you want to use it to control some motors, you should use the real-time operating system. Like I know that in Japan, iPron project is very popular in the Topaz project and the T-kernel, right? So if you want to control engines, motors, and so you should use real-time operating system. And if you want high performance, for example, if you have some hardware accelerators, like traditional DSP, FPGA, and some ASIC. Okay, because you want to get extreme performance, so you can find even no any OS inside, it's just a loop at the bare metal, right? So that is also required. And embedded virtualization is also, I will make a detailed introduction later. It's also a very important part. And the BIOS and the bootloader also belong different kind of plannings. So this is how we define OpenEuler embedded. It's just a big plus little. And the big brother is Linux, and the little brothers are a lot of components like real-time operating system, bare metal, whatever. So how can we put them together? We use, for example, infrastructure like a unified build, and we use rich features of Linux to get other planets attracted, and ecosystem and standard interface. So my conclusion here is that OpenEuler embedded is a complex and open and complex software embedded software platform, which is suitable that any place that require a complex OS like Linux. So this is our definition of OpenEuler embedded. Okay, let's go a little further to this architecture. From the bottom to up, in hardware level, we have more diverse hardware architecture than the IT scenario. For example, as we know, in the IT scenario, like server and cloud, there are just two main architectures: Intel's x86 and ARM, right? But if you get into the embedded world, you'll find that the world is more diverse. You can find ARM, you can find the x86, and you can find RISC-V. And as I know, in Japan, there are some architecture like Renaissance, like SH from Hitachi, right? They exist in Linux. So in hardware level, the world is more diversified. So, okay, let's see the application level. As I said, OpenEuler embedded is mainly for the OT scenarios. So our potential scenarios application including the PLC, robotics, energy, satellite, whatever. Yeah. So this is about application level. So to support this hardware and this application, this is the blue part is the scope of OpenEuler embedded. And we have a Fusion Dock. Fusion Dock can be viewed as OS for OS. It is a collection of different technology. It's not just one technology. Okay, bare metal, for example, in some heterogeneous processors. So it's okay. Virtualization, embedded virtualization, and the LibOS, heterogeneous, a lot of technology. So it depends on your hardware and scenarios. And as I said, okay, in OpenEuler embedded, there are not just one OS. In fact, it's a collection of OS. Although Linux is the big brother, but we also have some little brothers like RTOS, like bare metal. So in the big part, we chose Linux as some kind of de facto standard in embedded systems, right? But for the other part, they are more colorful. And here we list the UniProton is from OpenEuler OpenEuler community itself. Zephyr, a worldwide OS platform. Also, ArchiThread, China, well-known OS. And in Japan, of course, you can choose Itron, Topaz, Key Kernel, or whatever you want. So we have a lot of OS. And then we come to the MICA, the Mixed Criticality framework. It just like what happened in Docker. Yeah, we define MICA to provide abstraction about the Fusion Dock. Yeah, it can be different technology. And also we provide unified interface for the above OS. We define standard interface in Linux, and we define interface for small OS. So if you follow the interface we defined, you can easily get your OS or component get in. And another part is about infrastructure, like tools, like CI/CD, like build system, like QA. You know that other platform. Yeah, if you want it to be healthy, infrastructure is very important because each day developers or users will use it, and we use it to guarantee the quality. And we use the test, right? We use to cooperate. So the infrastructure is very important. Even OpenChain is some part of infrastructure because we should trace everything. Okay, this component is reliable, is secure, right? And this part is not shiny like the running part, run time, right? But it's just like iceberg below the sea. Although you can see it, but you can feel it every day, and it's very important. So this is the OpenEuler embedded architecture. Next is about key features. We name it. We summarize this 1 plus X plus 1. The 2, 1, as I said, we are a Linux embedded Linux distributions. So as I think that Linux means, we are, for example, 70% of the total system. So it's very important. We build our embedded Linux above OpenEuler's ecosystem. For example, we will have the same high quality, and we will maintain the kernel. For example, currently we used 5.10, and next we will go with OpenEuler community to the next LTS kernel, the 6.6, and we will do optimizations and customizations for the embedded scenario, which may be not killed by other scenarios like IT and CT. For example, the pre-IT part will be maintained by OpenEuler embedded, and we will provide better and more fine-grained config and tune for the kernel, right? And above, we will also have some, embedded related core components, like we use BusyBox, and we also may use Muscle C. These libraries are more embedded specific. And we also have embedded graphics, and we also have a package management system, but we don't put it in runtime. We just use it in build time. And we have embedded containers and the trace optimization. So this is a very important part of OpenAI embedded. It will be changed. It won't be changed. It will be always involved to the future. Another part is the infrastructure. I just said it's very important for a platform if you want to really it works, right? Like we have a cloud native based CI system, Compass CI, and we share all the repos management with other scenarios in OpenAI community. Yeah, so we share all the components. We have our own build framework. It's based on Yocto, but finally we will evolve to the unified build system, OpenMaker, and we have our own CI/CD systems. And then above them, you can find the SDK, because for most developers, they won't use so complex infrastructure. They daily work for user application. They will more rely on the SDK, and we have simulation, because for embedded system, hardware is very okay. I should debug my software in hardware, but sometimes you can't get the one, so you can rely on simulators like Tuning. Then we have online docs, and we have tutorials provided for developers, users, even students. So this is the infrastructure. It also won't be changed. We're always working on to improve it. And X means change, means something can be changed. Okay, from the bottom up, we already have several key features. The first one is soft bus. Soft bus is some kind of network protocol that's connecting different device nodes together. And it's come from our brother community, OpenHarmony. So we can use soft bus technology to connect the openEuler device and the OpenHarmony device, but also not limited to these two ecosystems, but also you can use to connect other ecosystems. So this is soft bus. For the mixed critical ID system, I just passed here because I will make a detailed describe later. And imported the runtime, imported the robot runtime. You know that the robot, especially in Japan, is very hot, right? A lot of people think that the robot will be common in the future, right? So we also put a lot of work on the embedded robot runtime. For example, we already successfully run those two above openEuler, not only in the server distribution, but also in the embedded distribution. And not only in the those two, we also, put some work related to industrial robot, for example, robot arm, also in OpenEuler embedded. And then, as I said, we will provide better and fine-grained customization for the robotic applications. And also, we will provide real-time guarantee with the technology and Mika to guarantee the real-time response of robot. So this is about robot. And we also have some two new phases in this year. One is embedded edge. We want to bring technology that is proven in IT area, like edge, like containers, into the traditional embedded system. So we will do the integration of Kubernetes, K3S, and EdgeX, right? So you can, with this framework, you can easily, let the edge device or no device talk with the cloud service. So with this, it will be easy for you to implement a good cooperation among cloud, edge, and node. So next, AI. So AI is so hot, so it's very important. But I think that if AI want to have more effect for us, it must be embedded systems. So AI. So for example, each device will be powered with AI. So that is also very important. And we will focus on the AI interference. And we will do the integration of mainstream AI framework and do optimization for this framework, like TensorFlow Lite, like PyTorch, like Mindstorm is from China. Okay. For the green part, are some new features we are scheduling. For example, eBPF, right? This is very popular in IT system. Rust. So we are also welcome the Rust technology in embedded systems. So as I said, we will continue to incubate new features and for new tech, new trends, and the new scenarios. Okay, this is the key features about openEuler embedded. Next is about the running model of openEuler embedded. It's a little technology specific. So this is we have 4 models to run in openEuler embedded. The first one is the most common and simplest, the single model. You just run one OS to do everything. But as I said, you cannot to implement high features and high reliability at the same time. Use one OS, right? It's very difficult. Then, okay, the next model is we call the AMP model. So we use 2 OS for different requirements. We use Linux for rich features and for safety, for real time, more related to real time. We use RTOS to implement it. But in the second model, the problem is that the real-time operating system and the embedded Linux are not isolated well. Yeah. So the problem is that the bugs or the attacks from the Linux can be easily affect the running of RTOS. So it can achieve, good performance like real time, but it cannot guarantee reliability or safety or security. So if you want to get that implemented, you should rely on next model we call virtualized model. Virtualized model. So we will rely on a hardware assisted virtualization technology like what is already very popular in ARM and x86, right? So we use a hypervisor. It's not a hypervisor like KVM or whatever. It's an embedded hypervisor designed for embedded scenarios. We use this to isolate different kind of runtime, like embedded, like a different OS. So they cannot together, and you just pay a little price for it. And but the problem of virtualized model is that it just suitable for homogeneous multi-core processors. For example, if it's a heterogeneous SoC or heterogeneous multi-core processors, the virtualization technology cannot cover it because heterogeneous virtualization is also a challenge, not only in industry but also in academia. So we will go to the last model, also the most complex model. We call fusion model. In the fusion model, you can find, okay, it's running about a multi-core SoC. It's already happens in some high-end embedded applications like automobile, like telecom systems, right? So there are many cores inside, heterogeneous. The GPU, NPU are all integrated. So you will find the software framework will be extreme complex. It will have hypervisors. It will have a lot of OS. It will have different runtime. So I think that is the trend of high-end embedded systems. Okay, this is the running model of openEuler embedded. Okay, this is the deployment scenarios of openEuler embedded. As I said, openEuler is not a simple OS, just like a small RTOS. It's a complex software platform, so it should be deployed in some complex scenarios. For example, it can be deployed with servers. So like in a server like Intel's Xeon, ARM's Quantum, so there are a lot of cores, right? So we use a Fusion dock to isolate different OS. Then you can run a server version inside. Then you can have good connection to the cloud or rich features. Then you can have openEuler embedded as a management OS. Okay, then you can put your critical applications into RTOS to do some real-time control or safety or security related work. So it can be deployed in server. Of course, it also can be deployed in edge device. For example, the bronze Xeon, or for example, NVIDIA's hardware, you can also deploy it. But the difference is that the number will be decreased. For example, in the server base, you will have tens of instance container inside, but in the edge, it will be just several, 2 or 3, right? Even more, or even less. So you can run, for example, in HMI, computer vision, and AI in OpenEuler edge or embedded. Then also you can run your safety or critical application into RTOS. So you can run it in edge base, and of course you can also run it in the node base. For example, for node base, if it has enough powerful hardware, you can also choose to deployment of 2 OS, but it will be simpler. For example, just 2 or 3 OS, not so many as edge as server did. So this is the deployment scenarios of OpenEuler embedded. And okay, the ecosystem of OpenEuler embedded. So, and for critical Linux components, we stand above OpenEuler community. Like as I said, the kernel, the software package, the infrastructure, we use everything to be shared in OpenEuler embedded. And our build system, currently, we are relying on Yocto. And I think that a lot of embedded companies will choose Yocto to make their distribution, because although it's very complex, but it's also powerful. And as I said, we also have non-Linux ecosystem, like bootloader, BIOS, real-time operating system, or whatever, hypervisor. And then we put these components together, it becomes OpenEuler embedded. Okay, then you can use in what kind of areas, like industrial IoT, robotics, energy, the board management controller of servers, AGL, no problem. Most popular embedded project can be rebuilt above OpenEuler embedded. So this is our ecosystem. Next, I will we just have 2.5 years history. I want to show some latest application of OpenEuler embedded in last year's OpenEuler Summit. So we have application in the industrial controller. Yeah, you can see that is based on our NPU, based on high silicon processor, and we have the support of EtherCAT, open standard. So we can use these to control servers. And we have a mobile robot solution in the electricity industry. We just let the mobile robot to patrol and for the security. And we have usually in a lot of UX with, for example, drones, robotic dogs. So it's equipped with OpenEuler embedded. And this is for the server scenario. Even in server, it has embedded controller. So this is BMC. There is a well-known open source project named OpenBMC, and we already support it in OpenEuler. And this is also an open source project that we will launch in this OpenEuler Development Day. We call it Euler Arm. It's a robotic arm, software-defined robotic arm. So you can use this arm to paint. So that is very interesting. Okay, come to the next part, also a very critical feature of OpenEuler embedded. You can see the red letters, MICA, Mixed Critical Additive Framework. Okay, general introduction of MICA. I think that mixed critical system is the future trend of high-end or whatever embedded systems. We can find this trend in a lot of scenarios. This is already happening, and this is what happened happening in the smart vehicles, from ECU architecture to domain controller and to the future central controller. So this is one trend. And in industrial application, we also find this trend from distributed PLC controller to the centralized PLC controller or virtual controller or cloud controller, you call it VPLC or cloud PLC. A robot arm for the end node device, for single node device, robot arm in the past just have, simple hardware, just several DSPs to control this movement. But if the robot arm equipped with a lot of cameras, leaders, it can become a smart robot arm. So its software will be complex. And drones also. So this is the openEuler embeds the definition of mixed critical systems. The hardware must be above multiple SoCs. Yeah, from 2 cores, 4 cores, and to even dozens of cores. And then we have a 15 block at the base to support different domains, and each domain has 1 or 2 or more OS instances. And we use Mika to connect different instances. So this is the architecture of a mixed criticality system in openEuler embedded. And we also have a 3-step plan for how to implement, how to support MCS. The first step is deployment. The second step is quarantine or isolation. The last step is scheduling, because we use scheduling to get better utilization of hardware, just like what happened in the IT systems. Okay, this is the general introduction of MCS. So the framework of Mika, there are just 2 paths and 2 important paths. The bottom is a 15 block, and the center is Mika. And there are 4 sub features of Mika, like life cycle management. We want the users can easily to start or stop or suspend the OS or runtime instance. Then next is the shared memory-based cross-OS communication. So we want different OS can communicate or can work together efficiently. So it's based on shared memory. And we will set up the service framework for different OS, which is we use Linux as the center, because Linux has enough infrastructure like what IO framework, like drivers, so it can be easy for Linux to provide service for other small OS. And another part is the infrastructure. How can we build different OS components together, just in one shot? As we know that the different OS, different runtime has different build systems. How to put them together is a challenge, right? If without such an infrastructure, it will be very challenging, very difficult for developers to make, mixed criticality related applications. So this is the framework of Mika. And we also have a roadmap for the Mika, and we start our initiatives since 2022. Yeah, we just use OpenMP as a base to do the proof of concept. And in last year and this year, our focus will be on the hardware-assisted virtualization. And of course, we can support KVM plus print RT-well. That is no problem. But as I said, in embedded system, we need parallel virtualization, even real-time virtualization. So this is our focus. And another focus is high priority focus is the infrastructure. As I said, a unified build of different components, right? And also a systematic description of different OS, how to allocate the resource among different OS. And also the DFX, like trace, like optimization, like performance tuning. We call it DFX. The DFX system for such a complex system. So this is also our high priority focus. Then we also have some middle priority focus. For example, lightweight container, but consider the latest trend, we will raise its priority. And libOS, we run a small OS in the user space of Linux. This is also a very interesting one. And some other implementation of Mika, for example, security, a key trust execution environment-based solution like ARMS TFA, trust zone. Like RISC-V, you can find the enclave, and in x86 there is SGX there. So we hope maybe in next year we can provide a well-defined, a good framework for the mixed critical system that which is based on heterogeneous multi-core hardware. Inside you will find OpenMP for the heterogeneous computing, real-time virtualization, lightweight container, and key. We put this everything together. That is a big challenge because you will find the software framework, even for embedded system, it's becoming so complicated, right? So this is our roadmap. And the demos, we already have some, POC demos of Mika. It's based on the cooperation between openEuler with Intel. We built this demo about Intel's, cutting edge x86 controllers. It's the 12th or 13th Intel core platform. It has a lot of cores, 12 or 16. Then we have Aiken on above them. Then we have, you can find how many OS here. One is we call Service OS. It's based on Ubuntu. And in the future, we want to use openEuler embedded to replace it. You can see the Windows VM for the human machine features. And we have RTVM. It's based on openEuler embedded with PRIN-RT patched. It also has a RTOS VM based on Zephyr. So that is really cool. So you can find in such just even one hardware, you can highly integrate different OS together. Just use one SoC to implement all the features. And of course, it also can be, implemented in ARMS architecture. For example, in inertial SoC, that's no problem, right? For example, we can use toppers to replace Zephyr because it's flexible. That is possible. I think that is also suitable for a lot of embedded application, even in the Japanese market. Okay, this is the demo about Mika. Okay, that's all.
Thank you very much.
When talking about the openEuler embedded, Dr. Ren can speak from 10 minutes to 4 hours. It's complicated, right? But every time after he gave the details, I will do an easy summary for that. We talk about a lot about Mika and openEuler embedded, but the basic idea is very, very simple. The embedded in the past is very simple, right? But nowadays, more and more embedded chipset become more and more complicated. Even now, the embedded chipset have 4 core or even 8 cores, right? So the basic idea is we can divide the SoC in different partitions. For example, if you have a 4 cores SoC chipset, you can separate maybe 1 core to run real embedded kernel, for example, Zephyr. Or even openEuler has also its own real-time kernel. We call it Unipron. You can run Unipron and leave 1 core as another partition. You can run maybe real-time thread, RT thread, and then leave 2 cores to run openEuler Linux embedded. So you have 3 partitions and run 3 different OS. Maybe you can use Zephyr or Unipro to control the break, to control some real-time job, and use another real-time real RT thread to do other some other devices. And also you can run the control part on top of Linux because Linux has a very good ecosystem, but Linux is not good at the real-time job. But we can put the different system into one chipset, into one SoC. So that is the basic idea for Mica. And this system can be used, you can see with some UAV, drone, or some control system, or even some industry production line or something like that. So that's the idea. If you have the idea, the picture, and then go back his slide, you will easy to understand that no matter how many ways to implement, you can use the visualization to do the partition, you can do the GeoHouse to do the partition, the key way to how to partition, make the SoC to different partition and run different OS on top of that. And between the different partition, Mica provides a message channel. You can communicate between the real-time world with the non-real-time world. So that's all. The idea is very simple, but the implementation, the details are a lot of details. So welcome, I think in Japan, Japan is very skillful in embedded system, a lot of devices, right? So I think, I hope there are more Japanese companies which can working with this technology to use it as a basic design or architecture to grow up a very big system. That's all. So any question for Dr. Ren?
I actually have one about crossing industry verticals. So I'm just going to unmute Zoom learning.
I have a question about crossing industry verticals. In lunchtime, we talked a little bit about embedded, but we also talked about specific areas like automotive. So it sounds like in general, this type of architectural approach to embedded would span different industries like automotive as much, yeah. And if you're doing automotive versus, let's say, smart home, do you need to change a lot, or is this basic architecture flexible enough that your time to market is very short?
Okay, I understand your questions. So I think that our framework is some kind of general framework. So the biggest difference in automotive is you have a specification. So you must follow AUTOSAR CP or AUTOSAR AP. So it's defined. So you must provide the same interface. So there's no problem. If our framework used in automotive scenario, okay, you just add adapters. I think that's what's already done in a lot of commercial companies.
Yeah.
So provide different adapters, interface adapters. Right, that's right. So in smart home, in consumer electronics, maybe there's no such a requirement. For what? Because it's simple. You know, in smart consumer device, it's very rare to find, okay, you need real features, but you also, I mean, reliability. Mobile phone is one. In fact, mobile phone is just like something like this mixed framework, because all your information, fingerprint, your face information are stored, not stored in iOS or Android. It's stored in a key environment. For example, trust zone, right? But just for security, right? So from this viewpoint, it's also something like a mixed framework. Yeah.
That's pretty clear. Thank you very much indeed. All right. Another hand for a wonderful presentation. And we're going to move on to our next presentation, which will move us to cloud. But before we go to cloud, I'm going to share my screen briefly because I wanted to tell you something.
Okay.
Yeah. Okay. We're going to do cloud in a second, but before we do cloud, we're going to steal. We'll be going back to your laptop, but I just wanted to steal this for a minute. So, I live a little bit away from here. I live in a place called Shikoku, and Shikoku is quite far away. But yeah, on the way here, something very interesting happened. I went to my local airport. This is a random story, by the way. Is this sharing? Okay. I went to my local airport and I found something quite fascinating. If I can open this, yes. I'll just make sure I'm sharing. My machine did some kind of weird reboot there. How very weird. And this is a random story. On my way to my local airport to come here today, I had quite a coincidence in that as I was coming here, and I'll share my screen, I found a private jet in Takamatsu Airport. And the interesting thing about this private jet is that it's completely secret who owns it. I checked all the records. I can't find out. It's marked as private. It's registered in Panama. But I checked the flight records. Whoever owns this jet has $82 million to buy it and flies it out of Hong Kong. So is it Jack Ma? Did he come and visit Takamatsu and have udon? I don't know, but quite a coincidence. Okay, back to business. We're going to do cloud architecture, and we're going to talk about how that works. For many of you, I think, in the Linux Foundation ecosystem, you'll know that cloud native is huge. And for many of you who are familiar with the China market, you'll know that, for instance, there are things like the Cloud Foundry, I believe, is quite popular and so on in China. Now, cloud technology presents an interesting challenge because it's inherently always online. It needs great security. The architecture can be very complex as we stack things. Just as embedded requires solid architecture, cloud does too. And we're going to have a look at how cloud native approaches in openEuler are planned out. And I believe this is quite a practical presentation as well, because as I understand it, in China, openEuler is used in the cloud in practice, in deployment. And for those of you who spend time in China, you'll know that the online services are very advanced. They're absolutely everywhere. So without further ado, let's welcome Zheng to the stage to talk about cloud native scenarios and case studies, architecting that, and the type of challenges. By the way, KubeCon is happening at the moment. Where is it happening?
Paris.
Paris. My goodness. Yeah, the team is out there. They said they're expecting 15,000 people at KubeCon.
Oh, I didn't share. Okay. I guess. Okay, I guess I got this share. So I think the good news is that some of these slides also shares at KubeCon in Paris. So we are quite synced. So I just removed most of the introduction parts, and we will get directly into the some technical details. As we just mentioned in the morning, and also the embedded part just mentioned by Dr. Ren, that the openEuler community is just beyond OS. Except the operating system itself, we actually have a lot of innovation projects from different areas. Like mentioned in the morning, we have Ola Copilot and GMM in the AI area, and we have Mika, LVM, and others for the embedded area. And to actually, the server and cloud native and edge part is also a very important part for the operating system. So we also have a lot of innovation projects in those areas. And we also have for the OS, for sure we have kernel innovations like just mentioned, and we have real-time kernel and other kernels, not just Linux kernels. And also we have as security is also here, right? We talk about it in the morning, and we also, because we have a lot of developers, the community also even have many innovations just for the development tools. So it's a very innovative platform for the whole community. And then now I will have a deep dive into the cloud native technologies, because I think embedded is also infrastructure, and as a cloud native era or intelligent era, the infrastructure is mostly on cloud. So probably there are some technologies you guys might be interested. So the first one I want to introduce is called Usura. We have already mentioned this in Dr. Ren's slides, and here is some details. Usura is a lightweight, fast, and flexible container solution. Comparing to other projects on the market, Usura is first, it is OCI Coughlan container runtime engine, and it emphasizes simplicity, robustness, and performance. And because most of the reason is because it's lightweight, and it tries to generate a unified architecture design to meet different requirements in the CT and IT fields. Because in the previous time, CT and IT fields are not so connected, and they have those chimneys for each of their services and solutions. But we are trying to make one unified design to meet for different scenarios. Like just mentioned by Dr. Ren, Usura can also be used in the embedded scenario because it's lightweighted. And also we provide a very strength in the northbound interface. It provides the CLI that can connect to Kubernetes, and as well as easy to use command lines. So it will be very easy to use, and you can plug in it to your current deployments. So it's very easy to use. And for the southbound interface, it supports OCI runtime and image specifications to make it smooth for replacements. And that makes it very easy to use. And it can also scale to a very large deployments. And it allows you to develop a customer plugin. And this is our logo. It's an ant, because Usura is a type of ant. So you can, if you are interested, you can try to Google it, and I think there are a lot of informations on Usura. And another project I want to introduce is called Strugglewort. It's actually also a lightweight virtualization technology. As mentioned, for cloud, you might want to use Docker, you might want to use the container, but for some of the services or business, you want to use virtual machines. And for virtual machines, all the lightweight and efficiency is also very important. So we have not only made the lightweight runtime for container, we have also made the lightweight runtime for virtualizations. And it's called Strugglewort, and it's as most of the openEuler innovation projects, those projects are enterprise grade technologies, you can use it directly to your production. And a lot of customers have already used Euler and StratoWorks in their production deployments. So StratoWorks is also a very lightweight virtualization platform. It uses a single, we are talking about uniform. So it can also use a single architecture to support VMs, containers, and serverless data center scenarios. And for the features, enhanced features, we have enhanced security because StratoWorks actually uses Rust language. I think is very popular or a very hot topic about Rust. So it's secure from the language level, and it supports SecComp to implement security isolation between multiple tenants. So that's security from different levels. And also, a very important thing for virtualization is that the noise or overhead, which occupies a lot of the resources for the whole deployments. So the very important feature for StratoWorks is the lightweight and low noise or low overhead. The simplified device model offers a very short startup time for just 50 milliseconds. And I think this can be compared with container engine right now, right? Because and the noise is less than 4 megabytes, and that's very small for virtual machines, because we know that virtual machines sometimes takes like minutes to start up, but we are doing very well. And so because of that, we can support serverless workloads for virtual machines with the security and isolation, but fast as container. So we have, because of that, we can also do a very fast scaling for our virtual machines. We can scaling within milliseconds. It provides a very flexible resource scaling capability for the workloads. And those two are the fundamental technologies for container and virtual machines. And besides of that, we have also incubated it to some solution level technologies or some deployments and management technologies. The first one is called KubeOS. It is a lightweight OS designed for the cloud native scenarios. And it leverages, KubeOS leverages the Kubernetes CRD plus operator extension mechanisms to create custom resources for OS. It can provide a unified management. The KubeOS can connect the OS to the cluster as a component. So the best part of this kind of solution and architecture is that we can use the Kubernetes to manage the OS and service containers. So we can upgrade versions and add patches or fix CVEs directly from the Kubernetes controller. So we don't have to do it one by one. We can do it using the Kubernetes controller, and then we can so that we can manage the OSs for all the nodes, as you can see from the graph. And we can do some collaborative scheduling. We can detect the cluster status before the OS changes to implement a collaborative scheduling of service and containers. Because I think that's also connected to the next technology I want to introduce. But I will say something here because for the recent years, the ARM architecture servers and PCs are becoming more and more popular. So for this, and each device, and also there have a lot of accelerator devices as GPU, NPU, and stuff like that. So how to make the most use of those hardware resources is becoming one of the critical issues that one can for the whole system deployments. So OS as the middle layer and connecting for the northbound, they connecting to the service, and for the southbound, they connecting to the hardwares. We are seeing that the OS is the one that unleashed the computing power of the hardwares. So in the qualitative scenario, we have to leverage the OS to connect to different kind of computing powers in order to make the most use of them. So the collaborating scheduling for the hardware capabilities for different hardwares and for the management control panel traffics and for the computer panel services, network panel services, and also for the real services is very important. So the collaborative scheduling could be very useful. And also we can provide an API O&M technology to have the Kubernetes native declarative API to use to manage those OSs in a standard manner. So if you, it's not only that you can control it from the Kubernetes, it's that you can write your own automatic management strategies through the APIs to let it work for you. And no matter, you can own with the AI technology growing these days, and I think it is also possible for AI to do those kind of things through the scripts. And also, this is provide a lightweight and security improvement for the previous technologies. And another, the next technology I want to introduce is also quite interesting for the scenarios that I mentioned, that we have a hybrid container deployment. That's, for example, we can see here, we have nodes and services that are, some of them are very high, with high traffic, but sometimes they have traffics that are not so real time. So sometimes we have to make most use of all the computing resources, and we have to optimize them and to assure the QoS for the services that needs more real-time handling. So Rubik can do those kind of things. And Rubik schedules and isolates resources to improve the node's resource utilization. And by the meantime, it can ensuring the QoS for mission critical services. And this is done by also with Kubernetes ecosystem. It is compatible with the cloud-native system. It's extended based on the extended API of the Kubernetes, so it is easily to use to your existing Kubernetes deployments. And now it can also provide an interference identification and control during the system is running. So you don't have to stop your current services. You can just do it in real time. And another one is that it's adaptive dynamic optimization. It's the performance of mission critical services can be optimized to ensure the efficiency and stable operation. But the ratio of resources for online and offline, offline means that services that are not needed so much real-time response, and it can be adjusted from this Rubik, and the QoS can be maintained. And it also supports custom extensions to give experienced developers or users more customized solutions. And the next one is the Eagle, and then this one is what I mentioned before, that if we have different clusters with different nodes and different operating systems, this Eagle tool can provide a production-ready large Kubernetes cluster automatic deployments and flexible and traceable manner. So you can control your clusters with different kind of workers, different kind of nodes, different kind of hardware technologies. So we can support x86 and ARM. And we can support a lot of OSs as OpenEuler, CentOS, and Ubuntu, and all of them are supported. And we can deploy it using either binary files and other files. And we can also support providing those online on your clouds. We can also doing this in your data center as an offline deployment. So it's very feasible up to you. And I think that's all for the technical details about cloud native innovation projects. And all of these projects are part of the OpenEuler community, but not you can use it with OpenEuler, but you can also use it without OpenEuler. So they are independent technologies from the OpenEuler community. So I think you are feel free to try, and there are some links about the details of each technology on the slides. I think Shen will send out the slides later, and you guys can check. And next, I will have some exposures for our next release. This is not the final version, but there give some ideas about it, and you can keep tracking. OpenEuler releases for every 6 months, as I mentioned, and in the coming months, OpenEuler will release the next major release. It's called 24.03. It is a LTS version. It's long-term support. So I guess it will have a very long time of support from the community and also from our OESPs and OSVs. And as we mentioned today, there are a lot of scenarios we can get. There are servers, cloud native and edge and embedded. Oh, this messed up. I will fix it. And we have also for the AI for OS and OS for AI part, for the AI part. And we have also different levels. As you can see that for different scenarios, we will have different improvements. Not in too much details, but that you can get the info. And for this different layer, we also have some big improvements. As for the kernel, we will use the latest 6.6 base kernel, and we will also update some of the top or most important libraries like GCC or glibc or OpenSSL to give you the, because we are talking about security the whole day, so updating them not only brings new feature, but also brings more security to the whole project. So I think you can feel free to track it, and we have actually have a very pretty website with the OpenEuler homepage, and we just updated our download get OS sites. We can have a look. Yes. We provide different types of OpenEuler, and for example, the base version is that you can get it from the get the ISO format, and you can install it no matter what kind of hardware you have. And we actually, sorry, let me. We also have a lot of cloud images, not only in Chinese cloud providers like Huawei Cloud, Tencent Cloud, and Ali Cloud. We also have cloud images on Amazon AWS, so feel free to check it. It's on. You can click here and get instructions. The image is now in the marketplace, so feel free to try it. And we have also a lot of container images on the Docker Hub or ORB stack, and also our own servers. And also, if you are using Windows and you want to have a very fast check, you can actually use WSL, Windows Subsystem for Linux, to try out openEuler and other innovation projects, since they have a very detailed instructions about how to do it. Actually, openEuler has been joined WSL for like almost 2 years, I think. So, and also if you want to use a VirtualBox, we also provide resources and instructions about. Or if you have a Raspberry Pi, you can also have a try. I think this will be very easy for you guys to try out. Okay, that's all I got, and I will show the link and okay.
I have one question about all the downloads. I noticed you support Raspberry Pi,
Yes,
which is an interesting one. Some years back in Japan, we had, as you probably know, a very large earthquake in March 2011. And about a year later, I started working on a project that became part of drone code. And one of the big challenges we had was that so much was destroyed, it was very hard to know where survivors had gone, what paths there were, and how people going into the disaster zone could optimize fuel. Now, at the time in 2011, we thought reconnaissance drones could be useful, but they were very expensive. The average price was about $14,000 for the cheapest. Now, when I say drone, I don't mean quadcopters, I mean fixed wing that can actually go a distance. So this project that became part of drone code was essentially someone who had actually a military reconnaissance drone contributed the hardware schematics to give a low-cost surveillance drone. We used what became, I think, PixPilot now. We used an operating system for drones, but we were using embedded boards, Raspberry Pi style boards for the actual computation, vision recognition and recording. And nowadays, Raspberry Pi is more than powerful enough to do incredible things. So even a long time ago, over 10 years ago, we were trying to use something like Raspberry Pi, and we were doing Linux distros on it. Debian, I think we used. But we had some challenges on not just the prototyping, but the deployments, because we were hacking stuff together. So it's interesting that, increasingly we have professional level platform technologies with strong architecture available for stuff like Raspberry Pi. And my lengthy question is just, when it comes down to the Raspberry Pi variant, is something even like that flexible enough for prototyping complex products or solutions? For instance, if someone wanted to take it and run computer vision for drones and so on, is it complete enough? Is there a lot of customization? Will it be expensive and time consuming?
Yeah, actually, I have a video on this computer, but it may take some time to find out. But I can tell you that for just 1 year before, on the because we will have the openEuler Developer Day on the end of May, right? And last year we were having it on April or March. On that event, we actually did a drone with Raspberry Pi and all the stuff you mentioned. And we also have a drone dog on the ground. And we have Dr. Ren just mentioned that we also have a pad with OpenHarmony on it. So all those three are connected together. So not only we can accomplish the drone go to some zones or some people need help, we can also, like the drone is taking the photo or picture, we can send the dogs from the ground to that point to get it on. I will find out the video to send it to you. So that's what we have already achieved last year with all the, it's not a product, but it's a prototype, it's very engineering stuff. Like the drones are, very, what's that? Very crafted or
They're not a finished product. They're just put together.
But the scenario, the use are very okay. We can do it live in the events venue, and I guess that's also what Dr. Ren mentioned, that we have a very good connection using the soft bus with different type of devices and do those kind of things. And we also have a scenario that's in the 2022's December. We also have that, is that a drone will detect if the mountain is on fire. It will detect and send back signals to OpenHarmony pads, and people can send out cars or trucks to those parts. But 6 months later, we can send out drone dogs. So that's very big improvements. And I think we will all continue to evolution on that on this year's OpenEuler Developer Day. Yeah.
It's a very interesting topic, not just because drones and disasters are very important in Japan, but it's a good case study, I guess, for the type of extremely complex integration that rapid prototyping is useful around. And it's nice, every piece of the prototype timescale we can reduce, that's great.
Yeah.
And let me do some explanation. So there's a boundary between the prototype and the community. The community does not do the prototype. We just provide some basic infrastructure and the technology. And all of the prototype and product. Some of the company in China has adopted our platform and make the product. But all of the POC and product are made by company.
Yeah.
So the relationship between the company and the community is we provide the infrastructure and the technology. And if the company use technology to do their product, and for the common part, we encourage they contribute back to the community, but it's not a force. You don't need to do that, but we recommend you do that. So if you ask us, do you know how they build the drone on top of openEuler? We don't know. We just provide the platform. On top of that, they made the drone and the dog and the robot and some of the robot to do that. So that is the boundary. For openEuler, we set up the rule that openEuler will not touch the application. We don't go upper to, we can go to the middleware level. For example, we integrate Robot OS, ROS 1 and 2 into openEuler. So openEuler is very easy for you to run ROS. But on top of ROS, we never do anything. We leave the buffer, leave the room to our production producer and designer. So that's the boundary between the community and the product. Otherwise, the community will has no boundary, will be endless. That will be killed the community. So that is our rule.
Yeah,
That's a very sensible rule.
Actually, I happen to find the video, so we can
Let's watch the robot dog.
Yeah, and you can see this is from this is installed with openEuler and Raspberry Pi, and this robot comes from this company. And this is the drawing, right? This one is with OpenHarmony, and this one is Raspberry Pi with OpenEuler. Yes. Yes, this is the drawing pad. It can connect to it uses softbus, and you can connect with the dog, right? This is takeoff. So the first one, this one is from the drone camera, and those two, this one is we take photo from outside, and this one is the drone dog's camera, and this one is our handset, the OpenHarmony handset. You can see that because we take photo on the screen, so it might be not clear, but yeah. We let him go to this H mark. Right? Yeah, that's one.
So in this case, the flying drone was giving some guidance to the robot drone, showing it where the H mark was.
Yes.
So the AI could orientate itself.
Yes.
So this kind of technology is very interesting. A long time ago, we had the early drone swarm. So around I guess 12 years ago or so, the US Navy did an interesting, what they called red team, blue team. And they had 50 quadcopters, red team, 50 blue team. And these 50 drones were fighting each other in theory. But in that case, all the drones were the same architecture. What's interesting here is two very different drone systems and AI collaborating to use computer vision and one ground machine using an air machine. I think that's going to be useful for us.
That's going to be useful for us.
It's kind of cool.
It's kind of cool. Yes, it's connected with the softbus Dr. Ren just mentioned.
What is amazing is that open source in general has allowed us to build on these type of technologies that previously 30 years ago, the only people who had enough money was military. Whether it was the American or the British or the Chinese military, the only people who had enough budget was military. And then gradually some really wealthy companies could do it. But now with open source, it's getting to the point where small companies, tiny companies can begin to play with these incredibly complex interactions because so much of the platform is already done. It's fascinating.
Yeah.
Those drone dogs are very interesting to me. I was first aware of the drone dogs with Boston Dynamics, with Spot. But then recently, because I'm weird, I was browsing Alibaba.com about 1.5 years ago, and I suddenly noticed that a ton of different approaches to drone dogs were being produced inside China, and quite easy to buy, not so expensive.
Yeah, kind of dog with a small robot and a small dream.
Yeah. I mean, even almost you could say disposable. So if you had a disaster or something, you lose 40, it's okay.
Yeah.
It's not that expensive.
Yeah, we actually have drones, not that high-end, but low-end drones, even only 100 RMBs.
So like 3 cups of coffee. That's amazing. So it's really cool that you're making the platform available
on so many different approaches. Like I saw
we can get it on VirtualBox as well as containers and so on. So we can just run it. That's nice.
Yes, and yeah, as mentioned, we just pushed it last year. Second half of last year, we got it on AWS, and we are still trying to make it on Azure and Google Cloud this year.
I suppose in practical terms, it means people can just spin up this operating system platform alongside others as they prototype and just check out what's working for them, which is nice.
Yeah. Yes, and actually, we got already a lot of subscribers on AWS.
Interesting.
Yes.
Interesting.
All right.
All right.
That's pretty cool.
That's pretty cool. Thank you very much.
May I ask the non-technical question?
Non-technical questions.
Any question?
I think there's a microphone up there.
I'll grab it. Oh, you got it.
So, this morning we discussed about compliance, license compliance and security stuff. So these activities, so cloud native activities and also embedded activities, they are using those process or tools.
Yeah.
Oh, so okay. What kind of things the engineer or contributor have to do with security or compliance?
Okay. It's a good question. Why we bring up the two cases, cloud and embedded in the afternoon, so that you show how we can combine the process and the real output. When you see the output, for example, embedded, maybe it including maybe 500 packages. Where the packet is from the packet pool. How the packet pool created and formed, it should go through the security and the compliance process. So how to do that? For example, you have an embedded version released, right? And also the packet pool is audited by for example, the security committee will audit the packet pool every day. For example, kernel have a CVE bug issue and bring up, and then the security team will quickly to say, hi, here the packet has a problem, we need to update and to patch it, and then the packet will be upgraded in the packet pool. And then, a lot of action will be triggered. For example, if I have embedded version published on our web homepage, and then if you adopt that, and we will have the CV alert to say, hi, your version, your release, embedded release will have affected by this CV. And you have to get the update very quickly and to update, to patch your system to upgrade. So from the audit the package to upgrade your product. So it's a wholly new, totally goes through a process.
Thank you for that. And another question is your contributor, openEuler's contributor. What kind of things they have to do? What? So to develop the new code in the openEuler project, so the contributor have something to do, for the license compliance and security stuff.
Yeah.
There are some other persons to check it, and the engineers, contributors don't have to take care about that license. What kinds of things happen?
Okay. So for compliance for the license, most of the developer, I think you don't need to worry about that because it's a precondition for the openEuler. Any package will go into openEuler's package pool. It should be tracked. If the license is complies with our rule, because we only take 70 license, we don't take the rest of the license. So any package go into openEuler's patent pool, it means it has conformed to our compliance rule. So but if you go out of openEuler, for example, we have this embedded release, and then you add something out of the patent pool. It's your right. It's out of
sorry.
control.
I'm not talking about that. I'm not talking about the user of the openEuler stuff.
Yeah.
I'm talking about the developer inside openEuler project. So you have many engineers in your project.
Yeah.
So there are any things to do by those engineers?
Okay. There are two kinds of engineers. One kind of engineer is, I don't write code. I just introduce a package software outside into openEuler. So that will you need to go through the precondition, right? And another is I wrote code in openEuler. I set up a project in openEuler. There are two kind of possibility. One is you can choose a license, but the license should be limited into the 17 kind of license. You cannot write a license by your hand. So hi, here license, and you adopt no. You only can choose 70 kind of inside one of the 70 license you can choose. This is the one possibility. The second possibility is if you don't make a choice of the license, the openEuler will grant default license. We will choose Mulan V2 license, which is also initialized from Beijing University and a lot of universities. They join together to have this license. But the license is do the verification with Apache V2. So they are the same. The grant, the right privilege is the same. So they are due evaluation or the certification. So if you don't write anything, so default, and then you sign the CRA, so it will be fall into Mulan V2. So the openEuler default license is the Mulan V2. So that's the two possibilities. Is it clear?
Oh yeah. How about the extra license? How about the security?
Security has nothing with the license. Security is
I mean, there are some procedure inside openEuler.
Yeah, right.
So there are some go through some tools scanning.
Yeah, right.
Each engineers, developers have to do something for that.
If you are, for example, if you are the maintainer of kernel, sometimes you will get some CVE inform the message to you, which is triggered by the security committee. They will send you. So hi, here is a problem. You need to fix it. And some of the CVE is from the NVD. We get together. We link with a lot of the NVD or some repo. We collect the CVE information, and then if we find this CVE affects our system, and we will make the identifier which seed and which packet will be affected, and then they will be informed. So that is developer. You don't need to do this proactively, but you need to wait. If some case assigned to you, depend on the level of security. I mentioned if the level is 9 and 10, you have to fix it and publish it in 3 days. So that was the job.
Okay.
Here is great. Oh, any question?
I think we are good. Let's have a coffee.
Okay.
Thank you. So for those of you online, that's the primary case studies done. We're going to have a coffee, and then we'll do a wrap up at 15:40.
So it's really complicated until now. It's
because you have a very good. So I'm just thinking of what kind of process.
Yeah, sure.
What kind of things are engineer?
So we can maybe the good way that we go through the process and also
就是虽然做了一个但是对公司这个 OS 来说，这个 OS 来说，你就是一个你自己写了一个，然后你其实对于很多发展来说，你这个自研的项目和其他外面的也是一样的。我跟一些小朋友，我跟你来分析。
Everything you find
So the article,
There are so many. Yes.
On the prototype,
Yes, in content. Yeah, right. I think yeah, I hope that like the other plan, it's a very good Yes.
这个是办法上的。对，所以就这个我们系统的这个
Okay, 40. All right.
So regardless on the line, talking about the robot, but you can't know that. Okay. 然后上面其实是有他们的信息。Actually, play it on the big screen. Oh, yeah. I'll just play it on the big screen.
Yeah. Well, it's on YouTube, so I'm gonna grab the video and I'll share it. For those of you who are online, we were just talking about something and I'm just going to share it for fun. So this will obviously be edited out of the final meeting, but it's something we're going to have a look at right now. So, all right. So yeah, let's have a look at Figure. So this is, I believe, proprietary.
Hey, Figure 1, what do you see right now?
I see a red apple on a plate in the center of the table, a drying rack with cups and a plate, and you standing nearby with your hand on the table.
Great. Can I have something to eat?
Sure thing.
Great. Can you explain why you did what you just did while you pick up this trash?
On it. So I gave you the apple because it's the only edible item I could provide you with from the table.
Great. So based on the scene right now, where do you think the dishes in front of you go next?
The dishes on the table, like that plate and cup, are likely to go into the drying rack next.
Great. Can you put them there?
Of course.
All right. So how do you think you did?
I think I did pretty well. The apple found its new owner, the trash is gone, and the tableware is right where it belongs.
I agree. Thanks, Figure 1.
You're welcome. If there's anything else you need help with, just let me know.
Isn't that cool?
The first day, I think that it will be applied in robotics.
In robotics.
Because, yeah, we cannot just use LLM to sing, to paint.
Right.
Yeah.
We need something useful.
That's right.
Now, of course, that's a constrained demo, so it's limited, but it's very interesting to see the potential.
So not only in the world, but also in China, the AI, especially robotics, are getting more and more attention, investment.
Yes.
That's right.
And in the beginning, probably a lot of it will be proprietary platforms like Figure 1, but over time, open source will be platform.
I think the same technology obstacle exist. Okay.
Yeah.
Large level ChatGPT is over there. Those OS is also already there.
Right.
So let's see how to make them together.
Yeah.
And innovation companies.
And what's interesting, I think, now is, for instance, figure 1, they were talking about the way that the mobility, the picking up of items and so on, that's self-taught. It optimizes.
Yeah.
So once we integrate enough that they can self-optimize, it becomes like a rolling.
That's right.
Yeah.
That's right.
That's cool. I was very impressed when I saw figure 1, but it's also kind of amazing and spooky that they told the LLM speak like a human. So it's like, I think I did well.
In fact, it's also the result of a lot of, free technology, like text to speech.
Exactly.
Right?
Yeah.
So,
it's very cool.
so now we have all together. So
We're at the intersection point.
This one, two things make me excited. One is the big one, another is success of Elon Musk. You can see
That was amazing.
That was amazing.
32 rockets, 100 tons.
That's right. That's right. It means that we got them. You can be in the damn Earth. Okay.
We can. We're actually able to move, and of course we're very lucky. The new space station is ready.
Unmuted.
Yeah, we had quite a few rocket launches, but the next generation rocket is having some difficulties.
That's right. That's right.
It blew up last night.
You have to see the rocket and almost destroy the base.
That was the new private one, yeah, the little one. But there's a replacement rocket getting ready as well from JAXA, but it's so difficult.
But I don't know why. Maybe this question is for you, and decades ago, Japan is very strong in aerospace. The H2 is growing, but decades later, 20 years Still H2, no change. Right.
Same in Europe. The
Yeah,
it's the Ariane 6 is still not.
Wow, that's right.
Yeah. It's like changing in the US. I mean,
Elon Musk is there, right?
well, apart from that, but like NASA's one, the SLS, it's really challenging. It still hasn't done the successful.
Yeah, that's right.
Yeah, it seems like we're all stuck except for Elon.
Yeah, as I said,
I stayed up.
last week. I just very excited to see the success of SpaceX. Okay, so I said, God, no, just the success, right? Okay, finally, they did a very fantastic job.
I think what impressed me was that one of the launch engineers was talking about the Starship, and of course it didn't make it down. It broke at about 83 kilometers. Didn't matter. But he was talking about the way they've got 6 more built behind.
Yeah, that's right. That's like a pipeline.
Yeah, they're building 6 more, and they're going to blow them up this year.
But although there are a lot of doubts, right, but it works.
It worked.
That's right.
32 rocket engines at the same time.
That's right.
Hot staging with 6 more engines. It worked.
Well, it works. Yes.
It's crazy.
That's crazy. The Soviet Union have never tried.
Right, because the Soviet one didn't work. They couldn't get all the
because it's complicated at that time. Without latest technology to make good computers, everything has to be.
It was because I was interested in the SpaceX Starship itself getting into re-entry. They just made a comment about it, which indicated that Starship was driving itself. They were like, and it's just adjusting its flaps now. So the machines are now able to respond on their own to environmental.
That's right.
Of course, in the Soviet time, we didn't have that.
Yeah, so it's too far. They could go for it. I mean,
I really want to visit the JAXA launch base. It's a dream of mine to go and see it.
It's in the island.
Yeah, it's down south.
So,
yeah, does that island belong to Tokyo though?
it belongs to Tokyo.
Yeah, but it's way down.
Yeah, that's
It's way down, but it belongs to Tokyo.
yeah, that's right.
Yeah.
When I was young, my parents used to work for the how to say, space center.
Really?
Yeah. So when I was young,
CLX, China Aerospace.
so in the Sichuan province, there's a city named Xichang. There, we launched a satellite. I go to the satellite center and I see the satellite, but it's a long distance from the launch pad. Yes. And we are in the room and just very thick window.
Oh yeah.
And almost 5 or 10 kilometers from the rocket. So I saw the rocket launch.
I think we've got two pads here. One is on the island, somewhere very south of Tokyo. Then there's one in Kagoshima. Yeah, that's the one that just blew up.
But last one, you said last one. Last one in the
Oh, was that Wakayama? Oh, that's fine then. Kagoshima's okay.
Kagoshima is the official.
Yeah.
Official.
Yeah. So Wakayama was the private one that just blew up. Okay,
They say it's success.
Oh, okay.
Who's the success?
But actually, I think for the engineers it is. They got data. So.
Yeah. The problem is that, so Japan Aerospace Agency is very strong in technology. The problem is they don't have the requirements. For example, for a year, just 1 or 2 launch. But for example, Elon Musk, hundreds of launches.
Right.
And also in China, also almost 16 or 18 launches per year.
So the cadence gives a lot more data, I think.
Yeah, that's right.
This is also something I think Europe is struggling with because the Ariane 5 depreciated.
Yeah.
There were only 6 left to launch over all the last history of 2 or 3 years. So then all the satellites are going to Mars, and that means no more data.
That's right. And before they can show okay, use this. Yeah.
I guess that's an interesting challenge, because if we launch more often, the manufacturing gets cheaper.
Well, yeah. So that's right. So why have one dream that one actually go to?
Yeah.
In what kind of form?
Yeah. I always said to people that if someone said to me, "Would you like to go to Mars?" I'd be like, "Yes, it's one way. It's okay. 90% chance it'll blow up. I don't care. I'll do it. Take me."
That's right. Yeah, a lot of crazy. In the world. Do you have any information they are using open source?
Oh yeah, actually I do. From NASA. So the drone helicopter on Mars.
Yes, it's space.
Yeah. And that was using a Qualcomm 600. Okay, so the NASA rocket's not at the moment, but SpaceX
they're using Linux.
Yeah. They have a customized Linux
to control the engine. Not only, but some non-critical parts.
Yeah.
They also use some data like the NumPy component. It's very famous in AI area. So in the SpaceX, in the Mars detector.
Right.
Yeah.
I'm not sure about the rockets. I just remember talking to one of the companies in Europe that was working on the Eurofighter. And the Eurofighter is quite old now, but it's inherently unstable. It needs over 100 corrections per second, or it will crash. So the computer system for that is such a specialized, fast, real time. And I guess it's the same for rocket, because you only have milliseconds.
So that's why you cannot. Because it doesn't require microsecond level real-time response.
But this goes kind of into one of your business areas, because it's like, oh, ASIC and stuff. Yeah, it's a curious one. But yeah, SpaceX has a Linux distro. I can't remember where they forked it from. I think it's a variant of Ubuntu that Tesla took, and I think SpaceX is using a similar.
That's right.
NASA's planning to use open source as a future robots. Because the drone on Mars was a huge thing. Because before that, it was using a PowerPC 730 chip, which is very low power, but it was shielded.
Yeah.
So expensive. But now they know they can use it. So, yeah. It looks like what they'll have now is
just like what happened in containers.
Exactly.
Hey, just 1,000 containers back that.
Right.
One crash doesn't work. Doesn't matter.
The Soviets had a very interesting thing. I think Russia continued it with a lot of their space technology was polling with 3 computers. And now with generic chips, like if you use a Linux-based robot, you could put 10 computers in it. It doesn't matter. The price is nothing. So I guess polling will be our way to survive cosmic rays. Yeah, that's so cool.
So this is also our. Let's go. We will bring container technology
to space.
And one hand just for simplify it. Another way is okay, just use numbers to conquer reality.
I had a conversation with a car company about this. They were talking about containers in cars, and I was like, really? And they were like, yeah, because of resilience. You just have multiple, they just die, spin up, you don't care, you don't know.
Yeah, the fact is they are not familiar with it.
Yeah, it's a huge leap.
Yeah, you know, when I will get different knowledge about container. Okay. This is what we need.
Yeah.
If you think that is easy to break, it's not the problem of technology. It's not, you don't know about it.
I remember there used to be a requirement from NASA that software would have 0 bugs.
That is too.
In the old days.
Okay.
And now I think we've realized that you just need lots of redundancy.
Yeah.
And if most systems agree, and the ones that don't agree, remove. It's very interesting. But yeah, so Kagoshima is still going. I can get to Kagoshima easily. There's a flight to Kochi. Sneak onto the rocket base.
It's open to civil.
Really, not the launch pad. Oh, okay. Oh, we can sneak in. Security is low. He says on a recorded live stream. Okay, it's wrapping up time, so I'll just wrap this up. So we're actually pretty much finished here today. We're just going to wrap up here, and I'm going to give you a very brief summary of why we did what we did. So I think the most important thing is that we came here today to talk about a professional area of open source that has not so many options. The professional area I'm talking about is having large platform technologies that allow you to build operating systems and solutions on top of them across multiple industry verticals. Now, about 15 years ago in open source, we had a lot of options in that area. Lots of different distributions and little communities springing up. Almost none of them survived. There was not enough scale. Either they depended on a single vendor, or they had a small ecosystem, but the ecosystem was usually constrained to one industry vertical, and they never got the momentum to continue over time. So in the modern market, we only have a handful of complete operating system platforms available. There are some choices out there. So one example is, for instance, the Android open source project. It builds on Linux. There's middleware. It's pretty effective. But there aren't that many. And today we want to look at openEuler as something coming out of China, which has already diversified into an ecosystem. And that's interesting. China is so big that you can incubate something and build an ecosystem that's quite large before you go international. So a lot of people, I think, aren't yet aware of this. They haven't had a chance to see this. And that's particularly important in a country like Japan, where, as we were just discussing during the coffee break, the embedded industry has a huge amount of prototyping. There's a huge amount of products to market, everything from industrial robots to smart homes, to trains, to nuclear reactors. And that means we have so many R&D teams testing and building stuff. Bringing awareness to them of another option for prototyping and building is pretty critical. Bringing awareness of something that has, from first principle, been architected around process management, using ISO standards like ISO 52330, working to use ISO standards like 18974. That means that a lot of the administrative burden of how do we tidy this up, how do we double check this, a lot of that is sort of done. And it's also noteworthy from our perspective in OpenChain, because doing that is a lot of work. And this is the first time such a big ecosystem has done this, and been in a position to talk in detail about it. This is the second operating system that has been involved in ISO 5230 conformance. The first one is OpenHarmony, and through the Eclipse Foundation. So your sister. And OpenHarmony, or enemy.
So
OpenHarmony was part of the Eclipse Foundation's transformation into using ISO 5230. So the whole Eclipse Foundation decided to use ISO 5230. OpenHarmony is placed with them in the Western world, and they self-certified. Now, what's very interesting about openEuler, forgive me if I'm wrong, but your market share scale is already very, very large, very rapid. I think your percentage scale might even be above OpenHarmony at this juncture. You're the biggest operating system in China. So the scale is bigger.
But also the
approach was different. Like
you didn't just self-certify, you had CAICT certify you. So it's like this other level of rigid approach, double checking, auditability, accountability. That's why it's interesting to OpenChain. And we started the day by going through some examples of the license compliance, the security approach, and then we drifted into, in practical terms, what does that mean? And we had a look at embedded and cloud. And in practical terms, it means a lot of prototyping can be done a lot more easily than ever before. That's nice. And with that in mind, we are at the beginning of a conversation. You know, this is the first time to begin to talk in Japan. We have some companies in Japan who came at the table. We had some companies who watched online. We have more companies that will watch these recordings. But it's going to take a while to build awareness and then build engagement and then build contribution. So this event today is a tiny first step. I think it was last year openEuler started to go international. And today was the first time openEuler came to Japan and opened the door to say, here's what we're up to. Completely open community, strong process management, check everything, audit everything, look at it, everything's open source, and you can be part of this. So it's the first step. So one thing I really liked is that, you know, we had this discussion that not only will we have the recordings of this event, but we'll also look at having written case studies, which we can then translate and give to people and share it over time. And I hope that in the future, we might invite some people from openEuler to do really technical deep dives into some aspects of how this works. We can do some online. Maybe we can do some virtual, some face-to-face, and not just in Japan. We, you know, have to go to Korea and talk as well. And I think this is an interesting point. So thank you very much for coming. Thank you for those watching live. Thank you for those who are going to watch the recording. And I'm sorry for everyone I tortured with photos of food and snacks that you couldn't have. So big hand to yourselves. Thank you.
Thank you, Shares, all of the arrangement, the meeting to prepare everything for us. Thank you for everyone being here.
Yes.
I think it's just mentioned, she mentioned it's just a tiny start. So we'll continue to do that.
Yeah, we have a lot to do. We've never seen something come as fast as this, I think. It's our first time to have an operating system appear this quickly with this much structure. So I'm very curious, it's 4 years in, where we can be in year 6 or year 8. Yeah. You know, this is not related to OpenChain GM. I'm going to download openEuler and run it in VirtualBox and play with it for my drone stuff. Japanese customer number 1.
Yeah, actually.
All right, those online, I'm going to exit the meeting now. So good day and have a beautiful one.
Okay.
All righty. Kabota's-san, by the way, sends his apologies. He got dragged into more meetings. That's the problem with returning to your office. There's no way out.